Sorry. Oh. I'm so sorry, everyone. Can you still hear out of at least one ear? All right, we're gonna get started. Hey, it's good to see here people in person. Yay. And for everyone on Zoom, welcome. I'm futzing with audio, so give me some feedback on Zoom. If you can't hear the audio, I will try to stand closer to the microphone or something. We're doing some crazy stuff here with the audio for those of you in Zoom. Progress. Okay, so today we're going to be looking at memory safety vulnerabilities. And I want to teach you about how to hack into computers and one of the most common sources of vulnerabilities. Okay, and I'm going to start with a little bit of material that I went too slow last lecture, and I'm going to try to catch up here about how computers work and how function calls happen in terms of what actually executes on your CPU. And we're going to dig into these low-level technical details because you need to understand that to be able to understand the source of where these vulnerabilities come from and how to exploit them. And then when I've given you a little bit of background, then we're going to look at some common flaws in software that have enabled people to hack machines. Okay, so we're going to start with assembly and call stack and what compilers, what code they actually write to make function calls work. We talked about last time about layout of memory, about registers. There's 3 special registers. 2 of them are used for keeping track of where the current stack frame is. And the stack frame is used for storing data that doesn't fit in the registers. And I'm going to show you how the computer keeps track of all this data. Okay, so it puts some stuff in registers while you're running the current function, but when that function returns, it needs to restore registers of the caller, so the caller has the stuff that it's expecting. So data needs to get moved in and out of memory between memory and the registers, and so we got to keep track of saving the data in memory when needed and putting it into registers when needed and keeping track of where in memory it is, and it's a lot of details. So I'm going to show you that. Okay, so let's suppose that we have a function, in this case main, that calls another function foo, the caller. And I'm going to show you how the call happens. When the function call happens, some stuff needs to happen. State about main needs to get saved with your space in the registers. And then foo is going to run. And then when foo finishes running, we need to restore all that stuff that got saved so that main can continue running. Okay? And the stack is going to be where we're going to be doing all the saving. So a calling convention describes how to do that, and it describes where to put arguments so that the callee knows where to look for the arguments to that function. Those are in x86, they're stored in memory in the stack. It's going to describe how you get a return value back from the function you called. In x86, the answer is that is in a register, in the EAX register. It's going to describe registers. When main calls foo, main was using the registers. Now foo wants to use the registers. So whatever data was left around in the registers from main has got to be saved. It's going to be saved on the stack. Whose responsibility is that? Is it up to main to do that, or is it up to foo to do that? We're going to describe how that happens. And also it's going to describe where local variables are stored. Okay, so there's the stack is composed of a bunch of stack frames. 1 frame per function that is on the stack factors. So when main is running, there's a stack frame for main, and then if main calls foo, we have a stack frame for main kind of saving some old stuff so we can come back to it. and then the stack frame for foo, the one that's currently executing. And then when foo finishes executing, we go back to the stack frame from main. Oh, thank you, Zoom people. Yes, I will remember not to walk away from the microphone. Okay, so let's get into it. The stack is a bunch of memory, and we're going to need to keep track of how it's divided into stack frames. Okay? And the one crucial thing is we got to remember which part of the stack consists of the current stack frame for the function that's currently executing. And that's so important that we got two registers set aside just for that purpose. The EBP and the ESP registers keep track of where the current stack frame begins and ends, okay? So EBP will point to the top in this picture, the highest address, the largest address, and ESP will point to the bottom, like the lowest, smallest address. And all the memory in between ESP to EBP is the current stack frame. Local variables and stuff that's saved and all that kind of stuff, okay? So the current function is going to refer to local variables a lot, so it's going to need to refer to the stuff in the current stack frame a lot, so these registers make it really quick and easy for it to access stuff in the current stack. EFP is the bottom of the stack. If you ever add something onto this stack frame, the way you do that is by pushing onto the stack, meaning you put it below where the current stack frame is, and then you adjust the bottom of the stack frame downward, which means like decrementing ESP. The other special registers we need to keep track of where in the code is currently executing, which instruction or which line of code is currently executing, and EAP will keep track of that. It's a pointer into the code section, the machine code, the compiled binary code of which instruction is being executed right now. Question?
In physical name, when we had environment diagrams, we had this thing called the flow, like a parent frame. So is there a concept of the parent frame?
Totally. Yes.
So is the parent frame like storing the address of where the parent?
Yeah, good. Well, yeah, absolutely. One of the things that's stored in the current stack frame is a pointer to the parent stack. Yeah, so it's like a linked list or a stack of these frames. And the register tells you where the very bottom of that is. And then within the stack frame, there's pointers to the next one, and that has a pointer to the next one, that has a pointer to the next one. So you can get back to the parent. Yeah.
Is EBP ever sustained?
Is EBP ever going to change? Yes. When we do a function call, we're going to allocate some space below the current stack frame for the function we're calling. We're going to move EBP down and ESP down. Yeah.
Let's say that like we're calling the next function in the middle of the current function.
Yeah.
How do we remember where we left off in the like previous function?
How do we remember, where we left off? Because we're like, if we're in the middle of one function and we call another one, we make a stack frame for that. We move EBP and ESP down. And then when that function we called is done, we got to like get back to where we were. How do we get back? We've already like overwritten the old value of EBP and ESP. Any ideas what might be some options? Save the EIP before you call. Save EIP save it somewhere so that we can restore it. Yes, that will help us figure out what instruction to go back to. You could imagine one thing you could do is you could have another register for the saved EIP. But wait, there's a problem with that. What's the problem with that? Yeah?
It gets overwritten.
Yeah, where do I save the saved EIP? I need a saved EIP. And then I will need a saved EIP. I need kind of an unlimited number of registers. So that's not going to work. So if I can't save the EIP in a register, where could I save it? I could save it in a global variable. I could save it in a global variable called the saved EIP. Wait, that's not going to work either. What's wrong with that? Yeah, what's wrong with that? Why is it not going to work to save it in a global variable? Same problem. I'm gonna need a save EIP and a save EIP. I need an unlimited number of them. So that's not gonna work either. A global variable also doesn't work, sadly. It's a really natural thing to try. So I can't save it in a register. I can't save it in global variable. There's only so many other places where you could save stuff. What's another option? You store on the stack because there's an unlimited number of stack frames. So one of the things we're going to save is we're going to save the EIP in the stack frame so that when you're done with the current function, you want to go back, you can look at that save value in the stack frame. Is there anything else that I need to save and restore, or is the EIP enough? Yeah? I need the EBP because I'm moving the EBP around, so I got to move it back. Yeah. Yeah, the ESP also I need a way to get back. So the simplest thing to do would be to save the ESP, but it turns out you don't need to save the ESP. Turns out that there's a way to undo the changes you made to the ESP and get back, but it's just kind of an optimization. Anything else I need to save? Yeah. It doesn't really matter. EIP stands for instruction pointer. That's the IP. The ESP, the SP stands for stack pointer. And BP, base pointer. Oh, thank you. Okay, so we decide, yes. Yeah, yeah, the E comes from when the architecture got extended from 16 bits to 32 bits, totally, yeah. Anything else we need to save? We decided that one of the things we're gonna need to save is the EIP, we're gonna need to save the EBP, and, well, the ESP, you know, in principle, yes, but in practice, no. Is that it? Anything else we need to save? Yeah? Local variables? Anything else? Yeah? Arguments? Anything else? Global variables you don't have to save because there's not a separate like copy of them for each different function. It's just the one global variable. It's the same for all the different functions. So those you don't have to save. Global variables are normally stored in memory, not in registers. So there's a global variable stored at some fixed place in memory. It'll always be the same place no matter what function is executing. So no need to save anything there. It's not stored in the stack. Global variables are stored in this section called data segment. Yeah?
That way you can't mess up previous things added to you.
Heap pointers. Maybe. Where would your heap pointers show up in this picture? Where would they be stored? Yeah, maybe I might have a local variable whose value is a heap pointer. So if I'm saving the local variables, it should be good. There's one more thing. There's one more thing we got to save. The registers. We got to save the contents of the registers. Okay, so you can watch as I show you these details. Hopefully you'll see how all these things get saved and then how they get restored. But that was like a crucial question. Yeah. Why we in practice don't see a ESP? It's an optimization. In principle, save ESP totally. In practice, we're going to see that you don't need to. All right. Maybe no more questions for now, so I'll keep going. All right, good. Let's look at how we're going to do this. So let me just kind of cut to the chase of how we're going to do this on x86. When we make a function call, the first thing that's going to happen is the caller is going to put the arguments on the stack. That's how where the callee knows to look for arguments. So the very first thing that happens is you start pushing the arguments on the stack in reverse order. So like the last argument appears highest at the largest address, and the first argument in this picture is going to be at the bottom, at the lowest number of addresses. So you just start pushing. The caller just starts pushing them on the stack. And the callee will know to look there. Then the next thing is, they said we have to save the EIP so that when the callee is done, code can transfer back to where we left off in the middle of the function. The way we do that is we push the EIP. We put the EIP onto the stack, onto the next unused part of the stack. And of course, when you push a value on the stack, you lower the ESP by 4 bytes to reflect that you just added 4 more bytes to the bottom of the stack. Okay, so now that EIP is saved. Sometimes we call that saved copy of the EIP the RIP. R meaning return instruction pointer. This is where to return to. When the function we're calling returns, it's going to go back to that address stored there on the stack, the RIP. Next thing is we have to save the EBP. What's actually going to happen is the caller is going to call the callee. There's going to do a function call. So now the code of the callee is going to start executing. And the first thing it's going to do is it's going to save another thing that has to be saved. We said the EBP has to be saved. So it's going to save the EBP. And the way it saves the EBP is by putting the old value of the EBP on the stack. Yes. It's now being, EBP is being saved in the callee's frame. This is your parent pointer. This is the pointer to the caller's stack frame. So when it's in the callee's stack frame, so it's there to keep track of when the callee returns. It's a way it can restore the EBP, or it's a way it can find the caller's stack frame. Yeah.
Why we're adding things on the stack down as opposed to going to higher registers?
No. The short answer is no. It's just a convention. You could do either way as long as everybody agrees. There's a little bit of a reason, which is that stack goes down, the heap goes up. They both grow. It's kind of nice that they grow in this way. So if your heap grows a lot and your stack grows a little, you got enough space. Or if your stack grows a lot and your heap grows a little, that's okay, you got enough space. If they both went in the same direction and I had to pick a starting point, then, like if the heap grew a lot, I might, it might kind of run over the stack, even though there would be space somewhere else. So it's just a little optimization. Okay. What is SFP? Remember I said RIP is just another way of referring to this saved EIP. We often call it the RIP. This saved copy of the EBP, we often call the SFP. Saved frame pointer. I don't know why it's not SBP. Sorry, there's like so much in computer science that's just like arbitrary and inconsistent and nah. But that's all it is. If you said old EBP, I would also totally know what you meant. Yeah. Yeah, it totally should be RBP, shouldn't it? Or it should be like SIP or something. Like, what the heck? I don't know. Sorry. Yeah, no reason. There's absolutely no reason as far as that. Okay. Good. Okay, so we saved these registers. Now, then we can update them. So we can update the EBP. Well, we've been updating ESP. We can update the EBP downward to point to the beginning of the callee stack. Okay, so the EBP now gets adjusted. So now we have a new stack frame for the callee. EBP points to the top of the current stack frame. Then at that place, you can find the SFP, which points to the top of the parent stack frame. ESP points to the bottom of the current stack frame. EIP points to the instructions that's currently being executed. Now, they're instructions at the start of the callee. And then we're ready, and we're ready to go. Well, we better make some space for local variables, so we make some space into the current stack frame for local variables. Then when the callee is done, we reverse everything. We go backwards. So we should just double check that all this can be reversed and undone and restored. The answer is we saved the EBP, so it can be restored. The ESP, all the steps that you did here where you were lowering the ESP, the callee does the reverse of that, increases the ESP exactly undo all that. So the ESP goes back to where it was. And the EIP is stored in memory on the stack. And so the CPU, we have a special instruction that causes the CPU to start executing instructions at that address that was saved. So we go back into the caller's code and continue running the call. So that's conceptually how function call and function return works. Question? Yeah, okay, good point. I don't actually know whether it's considered part of the callee or the caller stack frame. I think of it as the callees, part of the callee stack frame, but maybe I have some, I don't know if I'm saying that totally correctly. Sorry. Find that you found that, guess what? You found some limits of my knowledge. There are a lot of those limits. Okay. All right. That's conceptually. Now I'm going to do it again, but like with even more detail. Oh gosh. So stop me now if like the basic idea isn't making any sense. Because if the basic idea isn't making any sense, it's going to get a lot worse right now. Yeah.
Which way, we're actually in. Does it start at the dotted line and end up at the not dotted line?
So we start out, yeah. We start out with the current stack frame being this like top half part, right? So ESP and EVP kind of pointing up to the top half part. And where we want to end up is down, then pointing down in the bottom half. So we got to adjust ESP and EFP to make that adjustment. We've kind of been adjusting ESP downward, but so that's kind of going to happen, but we got to move the EBP down. So that's what happens in this step is the EBP gets moved down. Once we save the old EBP, then we update the value stored in the EBP register. So now it points to the bottom of this new stack frame that we've been constructing. Yeah.
I don't know how far ESP should go downwards.
How far should it go down?
Is it like
The compiler figures that out. There's got to be enough space for the arguments. You got to go down for the arguments. You got to go down for the RIP, for the SFP, and you got to go down for any local variables. So you just keep going down and down and down. So you've got enough space for all the things that got to be in there, and then you're good. And that's the compiler's job to keep track of that. And then when the function returns, the compiler undoes all that. For all the local variables, it moves it back up to restore the EBP. It moves it back up for the EIP. It knows how many arguments are passed, so it moves it. Yeah. Yes.
I imagine this is just like a simplified list, but is there ever a case where the stack gets so big that it reaches, that there's no longer space below it?
Yes. 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 And then your program crashes, hopefully, or something bad happens. It starts overwriting heap memory, and then you go haywire. Usually the operating system or the program sets up some safeguards so that if it goes down into the heap, then there'll be a crash. So if you did recursive function with the infinite recursion that never had any base case, you would keep pushing stack frames until you ran out of memory, and then you would crash, and you would probably get an error called stack overflow. And if you've ever used the website Stack Overflow, that's where the name of the website came from. All right, let me run through how this actually happens. I told you conceptually what we want to happen. How does it actually happen with machine instructions? What are the instructions the CPU executes to make this happen? The compiler is responsible for putting those instructions into your code when it compiles your program. So there's like all this stuff that has to happen. So the compiler's got to put in instructions to do all these things. And if you look at the assembly code of a compiled function, you will see instructions that do all these things. So you're going to be looking at assembly code as part of your project. So I want you to know when you look at this instruction to say, oh yeah, that's saving the EBP, or oh yeah, that saved the EIP, or whatever. So you know what those instructions. Okay. And who does what? These first three items here is the caller does that. And then the next items, the callee does that. And then the last one, removing the arguments, the caller does that. So a lot of the work is done by the callee. So you might have C code at the top, and then your compiler compiles that into assembly code shown on the right. So to highlight some things that are in this assembly code, you see this push $2? Want to make a guess what that is doing? Register. Pushing the arguments. How did you figure that out? Yeah, and the $, remember, means this is the constant number. And if you look up in the C code, the arguments were constants 1 and 2. So that's pushing the arguments. And then here is a call instruction. There's a specific instruction for making a function call, but it doesn't do most of these steps. It does only one of these steps. The only step that it does is it saves the EIP onto the stack, adjusts the ESP downward by 4, and then updates the EIP to the start of the callee function. That's what the call instruction does. So the next instruction that's going to execute after call instruction executes is this push instruction. What do you think this push instruction is doing here? Yeah, I'm looking for someone new who hasn't been super vocal. Yeah.
Add the value in EVP to the stack frame and then move it down by.
Yeah, save the value in the EVP on the stack frame and then move the ESP, the bottom of the stack frame, down by 4 to reflect that we've now got this extra thing in the stack frame. Totally. Okay, and so on and so forth. So let me walk you through it just step by step. We're going to start with the EIP starting to execute this first line of code. And here's a diagram of the stack. We'll just kind of like pictorially see what happens as you execute each instruction. Okay, so the first instruction pushes the last argument on the stack. So that gets written onto the stack, and then ESP gets reduced by 4 to reflect that we now added one more thing to the stack. And then we push the first argument. So that gets stored on the stack and ESP gets moved down. We call the caller, the callee. So that pushes the saved value of EIP on the stack, the ESP moves down, and the EIP gets updated so that next the CPU will start executing the code in the callee. But then this next instruction saves the value of EBP. It pushes it onto the stack. This is the beginning of a 3 instruction sequence that you can, like it's just a common pattern you'll find at the beginning of almost every function. So we give it a name called the function prologue. It's going to do these steps that I just showed you. So the push EBP will save the value of EBP onto the stack. So that's now, we now call it the SFP because it's saved, and moves the ESP down by 4 to make space for that. And then the next one, what does move ESP EBP do? Which register gets updated? Do you remember which register gets updated? Is this updating ESP or is it updating EBP? How many say it's updating ESP? How many say it's updating EBP? Yeah, absolutely. So in the syntax we're using here, the destination goes last. So this is updating EBP. So it's taking whatever value ESP is currently pointing to and makes EBP point to that. It's copying the value in ESP into EBP. So what that's going to do to the EBP register pointer is it's going to, does it move down or up? Down or up? Down to where the ESP is currently pointing. So it now points at the same place. So we just moved the EBP down. We saved the EBP, and then we moved it down to reflect we've got a new stack frame. And then we moved the ESP down by 4 more. Why do we do that? I can't remember why we do that. Sorry. I'm blanking out on that for the moment. Whew. Okay, that's the prologue. That's the beginning. Now all the code inside the callee starts to run. So the next part is whatever code is in callee, that will be compiled into instructions. I'm going to walk through all this and then I'll take your questions. I see you two waiting. I'm sorry. So then in this case, what the callee does is it does almost nothing. Oh, it has a local variable. Oh, now I know why we subtracted 4 from ESP. We need to make space in the stack frame for the local variable. And the compiler does that by moving ESP down to save some space for that local variable. So right below the SFP would be the local variable. Ah, yes. And then we execute the line of code in the callee, which says to return 42. Remember, the return value is passed in the EAX. So the way we do that is by putting the number 42 in EAX. And then we execute code to restore everything. The callee is now done. This is called the epilogue. It's basically the same 3 instructions will be found in every compiled program. Always does the same thing. It's got to undo all the stuff we just did. So how do you undo all of that? We gotta move the stack pointer back to where it was. So back to the top of the current stack frame. The EBP tells us where the top of the current stack frame is. And then we gotta restore EBP. It's saved on the stack. So we gotta look what is stored on the stack, wherever the ESP is currently pointing, retrieve that value and store it into EBP. And then move ESP up by 4. That's called the pop instruction. And then the ESP is now pointing to the return address, to RIP. So the last thing we do is this ret instruction. What it does is it looks where ESP is currently pointing, treats that as the saved EIP, and puts that value into EIP, and moves the stack pointer up by 4. So now the EIP will be pointing to the next instruction in the caller. And now at this point, everything's ready for the caller to continue executing. Its EBP and ESP have been restored back to what they were before. So they now point to the caller stack frame. The EIP has been restored to the next instruction after the call instruction, and the caller can continue executing. Okay, so that's the function call and the function returns. Now I'll take questions or comments or heckling or whatever's on your mind. Yeah. When you push the RIP onto the stack, yeah, right, yeah. The EIP, we adjust it to point to the next instruction after the call, and then we save that adjusted one on the stack. Yeah, yeah. It's not necessarily 4, because the call instruction might be less than or more than 4 bytes. I forget how many bytes it is. But it's however it's needed to get to the next instruction after the call. Yeah? It's arbitrary. Either way would be fine. This is a convention, meaning there are multiple conventions you could use that would all be fine. Everybody's got to agree on one. And it doesn't really matter which one you agree on. So this is the one we've all agreed on x86 with C code. Yeah.
Within every push and pop call, is there an implicit like add or subtract of ESP?
Yeah, every push implicitly subtracts 4 from the ESP, moves it down to reflect that you've added something onto the stack. Every pop implicitly adds 4 to reflect that you've removed something from the stack.
Is push a like a multi-line
It's an instruction that like internally you could think of it as executing 2 mini instructions. One is read from what's on the stack, and the other is subtract 4 from the ESP. And in fact, in the x86, most x86 processors have microcode, which is some like internal microassembly language, and each instruction here actually does multiple of those operations in microcode, but you're not allowed to program in microcode because they might change it at any time from one version of the processor to the next. They don't want to get locked into any of it. But yeah, totally. Yeah. Are we saving it? Well, the callee doesn't call any other functions, so it doesn't need to save it. But if it did make a function call, it would have to get well, it's already on the stack, so I guess we don't have to save it. These local variables are not stored in registers. There's space for them on the stack frame. So in some sense, they're already saved.
But we don't see those.
This is a really bad example because in this example, the callee has a local variable but doesn't use it. So the one place where it shows up is, see that subtract instruction, subtract 4? What that's doing is it's reserving space for the local variable. 4 bytes for that local variable. That's the only place it shows up. If this code actually used the local variable, you would see instructions in there that were reading and writing from that place in the stack. But I gave you such a simple toy example, you can't, sorry. I gotta take 2 questions and then I'm gonna keep moving, yes. Yeah, I don't know whether I should consider this part of the prologue. Maybe not, because that's dependent on each individual callee will have a different number of local variables, so it won't always be 4. Maybe that's not part of the prologue. I might have labeled that wrong. Why is it 4? Because in this case, the callee has a local variable that is declared as type int. And int is on a 32-bit platform is a 32-bit value, meaning 4 bytes. So we need 4 bytes to store that. So we subtract 4 bytes to reserve space for the int. In practice, you'll usually see it like this. There are actually like some funky instructions that got added at one point to try to like be one instruction for like all of this for the epilogue, but I think no one uses it and I don't know why. Anyway, I don't know. There's lots of details about assembly language optimization that I don't know, but I hope this gives you the main gist of things. And I think we desperately need a break. And I'm sorry for everyone who wants to ask for questions, but like, it's so hard to keep staying attention. So we desperately need a break. Let's take a 3-minute break and I'll be up here and answer questions if you want during the break. Do whatever you want, stretch, chill. Oh. Thank you for asking all these questions. I love it. Oh, yeah. When the colony is just about the first well, I was right about that. So it's always a mixed box. Exactly. Yeah. It actually doesn't. You could imagine how it's sounding. And that would be perfect. Oh, you don't need to. It's just left of. It's just remnants left of anyway. If the program is something correctly, it will never read anyway. So it's the same thing we have. We also write it under. There's certain places it's easier to write it, and some places it's harder to write it. So that's the only reason it's above. It's easier to write above. Could write it down. Pop. Pop. A value. He's a value at the start, but what he is pointing to, we have that 20 against class. And it moves this kind yeah. All right, let's keep going. Let's keep going. Y'all are serious troopers for sticking with me through such a ridiculously long lecture. I am so grateful to you. I've tried to listen to a lecture and I'm lasted 15 minutes. So the fact that you're still here means thank you. Okay, we're gonna keep going. So now I want to show you vulnerabilities. That was all background. I want to show you now some vulnerabilities in security vulnerabilities in programs and how they get hacked. When your browser has a drive-by vulnerability and you click on a link and oh no, there was some exploit because you have an unpatched version of the browser and it hacked your machine. How does that work? I'm going to show you how. Okay. So I'm going to show you buffer overflow vulnerabilities, which are one of the most common and cursed form of vulnerability in the history of computing. Okay, so I'm going to make up a story. It's not real. It's never actually happened. The details aren't actually correct, but I'm just going to try to give you some intuition for what a buffer overflow vulnerability is. I want you to imagine decades ago going to the airport, back when to like check in for a flight, you like gave your ticket to the, the customer service representative and they like pulled up your record in the computer system on their little terminal and like the record said what to do and they're like, oh, okay, yeah, I'll give you seat 27 on this flight or whatever, okay? So here's what the terminal that the customer service representative sees might show them. You give them your name, you walk up and say, hi, I'm Alice Smith, I'm on the flight 293, and the customer service representative looks you up and says, oh yeah, sure enough, we got you in the system, Alice Smith, you're in economy, you're on flight 293, that's leaving at 8:50 a.m. You're all set to go, here's your ticket, okay? And they assign you a seat, they pick out a seat for you in economy and they hand you a ticket with that. I want you to just imagine a system that works this way. It's not how systems work today, but we're in a thought experiment here. And I want you to imagine that, suppose that the next time you fly, you go to enter in your name on the website, but you like take a micro nap, partly through typing the last part of your name, or your cat like jumps on you and you hold down the H key. And now instead of entering your name as Alice Smith, it's Alice Smith. Okay, so you add up with a whole bunch of H's in your record and you go to the airport. What does the customer service representative see? They see this on their terminal. They see Alice Smith with a whole bunch of H's, so many H's that it wrapped around. And in this case, in this example, the software was coded in such a way that it started to write over the next line, and it says you're in economy class. All right, I want you to imagine the system worked this way. And now think about how, this is a bug. This is a bug. Think about how you, as a malicious airline passenger, as Alice Smith, could exploit this bug in the system the next time you fly. And I want you to turn to someone sitting next to you and talk to them about how you might exploit this. What kind of malicious thing could you do and what could it enable you to do? Okay, talk to a neighbor. All right, let's check in on you. Does someone want to share something that you could do by exploiting this bug you and your partner came up with? You've been selected.
We like thought about if you can figure out how many H's you need in the box, or I guess not even how many, but you type like an atrocious amount of H's, and then at the end of your like tons of H's, you type first class, so that like it basically just like overrides all of the economy and just puts first class, maybe with a few H's in front of it.
Yeah, cheapo first class tickets, and then you get assigned a seat in first class.
As opposed to using a quote atrocious amount of H's, you could also use spaces to make it less ambiguous.
You could put spaces so it doesn't look so weird to the customer service representative and they're not even suspicious. You just put exactly the right number of spaces and then you put first class and they won't even notice anything. And yeah.
But also like overflow enough, you go to a special instruction, right? Like plus one. You have someone else in with you.
Yeah, special instructions, like make sure to give this passenger a free glass of champagne or something. Yeah, yeah. Okay, how many of you came up with something like this? Okay, good job. You did two things. You thought like an attacker. That's something we want to teach you. And you hacked your first computer program. Well, maybe not your first for some of you. Well done. Okay, so you are now officially certified hacker. Okay, good. So we could put some spaces in or whatever, exactly the right number, put in first class in there, hooray, awesome. So this would be an example of a buffer overflow exploit where this code should have checked the length of the name, but allowed the name to start like overflowing past the end of the field that was intended for the name and start overwriting some other stuff on the screen. And that other stuff was important. And an attacker could exploit that by exploiting the lack of the checks in the code to provide some very long value that starts overwriting other important stuff, and the attacker now can control stuff they shouldn't be able to control. Okay, so that's the principle of a buffer overflow attack, but we're going to see how it actually arises in software. This is like such a special case. Like, this is like a 1 in a million. If this was all there was, it wouldn't be that big a deal, because like, you know, how many software programs would really be vulnerable to something like this? Not that many. But it's far worse. Okay. How does this show up in low level in programs? Well, if we're writing like C code, you can have C code that looks like this and the compiler will accept it and execute it. You can declare an array that has space for 4 bytes, but then tell the computer to write to some index that is past the end of where there was space allocated for it. And the computer will gladly go ahead and do that. There's no bounds checking. In Java, the compiler inserts some extra code to check whether that 5 was within the range of this allocated memory. But in C, there's no checking that's done. The compiler just trusts you. And remember that C has no notion of like, I don't know, the type or length of array or anything like that. It's just the sequence of bytes. So it'll gladly just go start writing to memory. In this case, past the end of what was allocated for this array. Who knows, maybe that was some other data was being stored there and other data now just got overwritten. Okay, so if you write code that allows an attacker to start writing in a location and you don't have any end condition that stops when the attacker forces the attacker to stop when they hit the end of the space allocated for this array, but allows them to keep specifying longer last name and keep writing and writing and writing past the end, they can overwrite other parts of memory where other important things might be stored. And that's called the buffer overflow vulnerability. The buffer here is the array name. The overflow is writing past the end of it. Or past the beginning would also be, but past the end in this case. So here's an example of some code that is vulnerable, some C code that is like a classic example that's vulnerable. In this C code, there is an array with 20 bytes allocated for that array. And then this code calls a standard library function getS. How many of you have heard of the getS function? Yes, I'm so glad that almost no one has heard of this. This is a function that should die. It is because it is unsafe. And so we've been trying to get rid of this function for a while. So I'm delighted that you haven't heard of it. This function reads in some text from the input and stores it, in this case, into the name, at that place name. And you'll notice that you don't pass any argument to getS saying how much space is available or how many bytes to read. It just reads characters until it hits a new line, as long and as short as that might be. So this is vulnerable because if the input has a very long line that contains more than 19 or 20 characters, it'll read all of them and it'll keep writing and it'll keep writing and writing and writing and writing past the end of the name array into whatever else happens to be stored in memory after it. And this could cause any number of things to happen. It could cause other variables to get trashed. It could cause your program to just crash with like a segmentation violation because memory got access that wasn't supposed to be. Bad things can happen. Okay, so this would be an example of vulnerable code with a vulnerability. And if you write your code this way, you've now got a security vulnerability in your program. It's vulnerable to buffer overflow exploit. Yes, good. Website reminded you don't use that because if you do, you'll be vulnerable. There's no way to use it safely. Okay. That was a bad example because there was nothing really stored in memory maybe after name, so maybe there was not much harm done. If there's nothing in memory after name and you start overwriting unused memory, who cares? But let me give you, maybe it's a slightly better instruction that gives you a slightly better example that gives you some intuition. Suppose there is something else stored in memory right after name. There's these special instructions. Then if the name is too long, it starts overwriting the special instructions. And I could specify that my name is David Wagner, a bunch of spaces, and then make sure to give him a free glass of champagne when he boards. Okay, so that would be a buffer overrun vulnerability, very analogous to this made up story that I just showed you with airport check. That still doesn't seem so bad. I mean, I got a free glass of champagne, but you know, big deal, not that big a deal. But it can be worse. Oh yeah, I guess I should show you why this works, like what happens, what memory looks like. If we have this code here, this global variable name gets stored in memory. There's 20 bytes for that, so that's 5 4-byte words. And then right after it is the space for the instructs variable, so that's another 5 4-byte words. So that's just contiguous memory. And getS starts writing at the beginning of name and keeps writing for as long as there's stuff in the current line. So it can keep writing past the end of name and start writing into instructs. All right. Here's maybe a better example. Suppose that what's stored after name is a global variable that indicates whether or not The user has authenticated with special administrator access privileges. And normally the answer is 0, but if the user like enters in the administrator password, then it remembers that they've authenticated, sets that authenticated value to 1, and now they can do other actions. Well, now this code has a serious security vulnerability. If I provide a name, David Wagner, some spaces, and then with the right number of spaces, and then something that will cause the value 1 to be written right after the end of the name array to overwrite the value of authenticated. Now the value of that global variable authenticated got changed to 1. And now there might be other logic in the code that is now going to treat me as authenticated as an administrator and allow me to have administrator access, even though I shouldn't have had administrator access. Okay, so it's not just me getting access to like a free glass of champagne, but I got administrator rights on that program or that machine, if the rest of the code is using that authenticated variable for access control.
How does an attacker know how many spaces, for example?
How does an attacker know how many spaces to write? Any ideas? If you're an attacker and you like kind of hypothesize something like this is going on, how do you know how many spaces to put? Yeah? Do all of them. Say more. Just keep trying. Yeah, like try 1 space. Did that work? No, I'll try 2 spaces. That's reasonable. Yeah. Any other options? Yeah.
Knowing a bit about the system that they're using helpful?
If knowing a little bit about the system could be helpful. If this is open source software, or if it's paid software that anyone can download and install, then the attacker could get their own copy of this software, look at the code or look at the compiled assembly code and figure out that that's a 20 byte variable. And so we need enough spaces to make it out to exactly 20 bytes. And then we can start overwriting authenticated. And you'll do that in project 1. Yeah.
And wouldn't it be suspicious if someone's like submitting like only 1 space or 2 spaces and they have like so many different entities?
If there's a human looking at all these interactions, that might be suspicious, but usually these servers run unattended with no human checking what's happening. We couldn't possibly. Amazon's handling, 1 million transactions a day. There's no human looking at every single one. So most software systems don't have any mechanism by which anyone would notice to be suspicious. And computers don't get suspicious. They just do what they're told. Yeah.
In this case, if the array was written above the executed variable.
What if they were in the other order? Yeah. So you can see how the memory layout can influence how serious a vulnerability this is. If they were in the other order, this would not be a serious vulnerability. Yeah, so it all depends. But what I'm going to show you to come in the rest of this lecture, maybe the next lecture, maybe some experience in project 1, it turns out that in the huge majority of cases, there is other stuff in memory that's really sensitive and that is enough for an attacker to do really nasty things. So while this example is not enough to show you that, there's enough stuff going on in programs that it turns out you're basically always hosed if an attacker can write past the end of it. Not always, but almost always, just like. But maybe that doesn't seem very serious, because how often is it that we have a global variable with a name and a global variable with an authenticated flag, and they just happen to be right after each other? Maybe give you a little more intuition to give you a little more feeling for like why this could be a common problem. It doesn't have to just be an authenticated variable. It could be some like shell command that later the program is going to run. The attacker overwrites that shell command and then now runs that program, and it's not running the intended one, it's running one the attacker specified. The attacker can now run any command on your machine. It could be, and this is the real one that usually gets you. Let's suppose there's a function pointer stored in memory right after that array. And at some point, the program is going to call that function pointer. Why is that really dangerous? Why does that give the attacker a lot of power? Yeah?
If there's any other vulnerability that lets them basically add a function into the memory, then and they can change this one, they can always point to their own function.
Yeah, the attacker can overwrite the function pointer with any other address, and this program will start executing code at that address. So if there's some really bad, dangerous stuff somewhere in the code segment, could point this function pointer to point at that. And if there's not some really bad, dangerous thing, if there's some way the attacker can get the attacker's code into memory somewhere, and then point the function pointer to point to that copy of the attacker's code, then this will start executing the attacker's code. Did I get you there? I just did a kind of a weird twist. Are you with me, or? How could, I see a question. I'm gonna come back to you. How could an attacker get their code into memory? They don't have they can run the program, provide inputs to the program, but they can't like directly modify the memory of this program. How can an attacker get their malicious code, their evil code, into the memory address space of this program? Yeah, back there, yeah. You in the white, yeah. Instead of the attacker providing their name, they pretend their name is the byte sequence of the malicious code. And that gets written into the name array. And then they overwrite the function pointer to point to the start of the name array where they just arranged to have their malicious code copied into memory. So this program is already copying from its input into memory anything that's provided. So the attacker could provide malicious shellcode as the thing to copy. This program will gladly copy it for you.
Not the outside of like where they.
Yes, good. Okay, love it. Awesome. As of 1980s, 1990s, around 2000, the operating system would gladly let the program run code anywhere in memory without regard to where it is. You'll notice that this exploit we just described involved getting some malicious code somewhere into the global data segment, which is not where code should live, and then causing the CPU to start executing there. That is a really weird thing to do. That's like, should never happen, right? So this is one of the defenses, and we'll talk about it. We'll talk about this defense of limiting what code the CPU will run. For instance, CPU should never run code from the data segment where global variables live. It should only run code from the code segment. We'll come to that. There's defenses and then there's attacks in those defenses. And for now, I want to keep it simple. So we're going to like start with no defenses and we'll build up. We'll build up to it. But yes, totally. Okay. So this kind of code here, if you have code like this, just like the absolute worst disaster. Anyone who can supply input to this program can now totally take over control of this program and cause the program to do anything else that the attacker wanted. And that is the common case with a buffer overrun exploit. When you have a buffer overrun exploit, often there's a way to do something like this. Okay, let's look at it. Let's get a little more concrete though. That was like a theoretical example that something bad that could happen if the code was written in just the wrong way. Now we'll look at what happens in practice with like more typical looking code. Turns out that this vulnerability is arguably the worst class of security vulnerabilities of all time. In 2023, it's the #1 on the list of most common, most dangerous classes of security vulnerabilities. Super prevalent, super common. Fortunately, becoming less common after 30 years of getting hacked by these kinds of vulnerabilities. We've started to put in place some defenses and we've started to learn something about how to not make these mistakes, but it's still a problem today. So I'm going to show you how to exploit real programs that have these kinds of vulnerabilities. And I'm going to like introduce some notation here. We'll use like Python syntax to represent strings. It's just be convenient. So if I write like quotes A times 5, that's a way of saying 5 copies of A. It's just like simpler than writing 5 A's. Well, 5 A's would be fine, but if I had 32 A's, it would get tedious. And also as a reminder in Python that you can write byte values if you do \x, and then you can write a byte value in hexadecimal. So it lets you put arbitrary bytes even if they're not easily representable in ASCII or if you don't know what like letter they correspond to. So this is a way that we can represent arbitrary byte sequences too. So I'm going to show you the first type of exploit against buffer overrun vulnerabilities. If your code has a buffer overrun vulnerability, the oldest form of vulnerability and exploit is called stack smashing. And this stack smashing occurs if I have a array or a buffer, a memory region that's stored on the stack. The examples I showed you before, the name array was a global variable, but let's suppose it was a local variable, so it's stored on the stack. That's when stack smashing becomes a problem. If you have an array or a buffer that's stored on the stack and there's some code that doesn't do proper bounds checking and allows the attacker to write outside, like past the end of that array, you have a stack smashing vulnerability. And there are various techniques to exploit those stack smashing vulnerabilities. In that case, if your code has that vulnerability, the attacker can start overwriting stuff after the end of that array. What's some other stuff that's also on the stack that might be after that array? All the things we've been talking about that are on the stack. SFP, RIP, local variables, arguments, all that could be overwritten. Does anyone have an opinion about which of these might be juiciest for an attacker to overwrite? I mean, any of them could be juicy in principle. I'm looking around to see if there's anyone who hasn't been answering a lot, just to give you all a chance. Yeah? Yeah, RIP is really juicy thing to overwrite because you put some other address to some other code. That might be any malicious thing the attacker wants. So the RIP is going to be a really juicy thing to overwrite. So the stack smashing exploit typically involves overwriting an RIP. So to help understand how this exploit works, we gotta look at what's on the stack. And let's suppose we have some very simple vulnerable code. This is like the simplest possible example of code that's vulnerable. There's a getS call, vulnerable. We'll write past the end of name. Name is a local variable, so it's stored on the stack. So we have this picture here where there's a stack frame for this current function. And that stack frame has space for the local variable, and it has the SFP stored on it, it has the RIP, and then above that is like the caller stack frame. So if an attacker supplies a long name and starts writing past the end of the name array, what's the first stuff that gets overwritten? Yeah, SFP. The SFP is the very next thing after the end of name. It's the very after means higher addresses, larger addresses, so up. So SFP is the next thing that gets overwritten. And then what gets overwritten after that? EIP, the RIP. So if you provided input to this that was really long and was just random characters, the SFP and the RIP would get overwritten with random stuff. And what would happen after getS finished and this function returned? Well, I don't know about that. It's not like the CPU says, I don't know what to do, I'm stuck, I'm in trouble. Instead, the CPU just does whatever it's told to do. Yeah?
It'll go to whatever function that the hacker is telling it to.
Let's suppose no hacker, just random characters, not even an attack. Yeah?
We'll look at the value of RIP, go to wherever.
Whatever's now stored in RIP. And what's now stored in RIP?
Whatever
Whatever got put in as the input at that locate part of the input. So probably some random character. So it's probably like some random address or something. Most likely it doesn't point to anywhere valid in memory. What most likely happens is your CPU tries to start executing there. There's no, like that part of memory is not used, and it's like segmentation fault, program crashes. Can't execute, there's nothing in memory there. Failure. So if you have this kind of bug in your code and you just do some testing with some random names, you might find your program crashes. But an attacker who's malicious, instead of putting random things in, could put some very specifically crafted characters to replace the RIP with an address that the attacker chooses to cause the instruction, the execution of the CPU to transfer to some address that the attacker chooses where there's some malicious code residing. Okay? So suppose the attacker somehow has arranged or knows that at this address, hex deadbeef, that there's some code that will do something really damaging. And the attacker wants to get that code executed. What the attacker can do is try to overwrite the RIP with that address, deadbeef. Okay? Tell me about the input to this program that the attacker should provide to arrange to overwrite the RIP with deadbeef. First, how long does that input need to be? And then tell me what that input needs to be. What needs to be true about the input? Talk to your neighbor and see if you can figure that out. All right, let's see where y'all are at. What is the minimum length that the input needs to be to achieve these goals? What do you come up with? You can just shout it out. I heard a lot of 28s. I heard a 25. Anyone going for anything other than 28? 24? Someone want to give me a reason why 24 might be a reasonable answer? Yeah? Yeah. Yeah, so 24 would be enough to overwrite the SFP. So it's kind of like, oh, I guess I really want 24 plus some more, because 24 and then some more to overwrite the RRP. Okay, so how many more? I guess there's 4 more for RRP. So are we with 28 is reasonable? All right, and what condition do I need to be true if I want to overwrite the RIP with hex deadbeef? What needs to be true about the input for that to happen? Yeah? The last 4 bytes, the bytes 25 to 28 need to be deadbeef. And by the way, big endian or little endian? Little endian. So we got to get the bytes in the right order. Okay, good. Yes, so that will be the basic exploitation strategy. Here is we provide an input that is like basically 20 bytes to overwrite name, 4 more bytes to overwrite SFP. That's like your padding that we had to do, the space we had to do, and then 4 more bytes to overwrite the RIP with the address that we want to get in there. And if we do that, when this function returns, the CPU will start executing instructions at deadbeef. Now you might notice that when it starts executing instructions at deadbeef, the SFP was messed up, so the EBP that gets restored when this function returns will be messed up. So it starts executing with a messed up EBP. So we better arrange that whatever the instructions at deadbeef, if the attacker wants to cause some harm, they better arrange that the instructions at deadbeef don't rely on EBP to be correct. But if the attacker is writing that code, the attacker can certainly write that code. That doesn't need EBP to be correct. So they can write malicious code where the EBP is messed up and the malicious code still works. Yeah. Yeah, what if arrays went the opposite way? Would that affect? It totally would affect this. And it's kind of convenient for the attacker that they go the direction they do, because it's always true that right after this local variable is an RIP, you would have to work there. There were other architectures like Spark where I think it went the opposite direction, and as an attacker, you had to work a little harder. But it was still sometimes possible to do, maybe not always. But I'm trying to make your life simple here. There's like any number of complex situations that could arise where like exploitation becomes more difficult. So I'm showing you the easy path for the attacker so that you can understand the basic ideas. And then sometimes in real software, you'll find there's all these constraints that make it difficult. And it's like this complex puzzle. Can I get all the pieces to work together as an attacker so that I can make an exploit work? Sometimes you can, sometimes you can't. Yes. Yeah, the attacker could arrange to make that the bytes, the first 20 bytes could be anything. The next 4 bytes, if they needed EBP to have a certain value, they could arrange the next 4 bytes of their input were whatever value they want to have in the EBP, if they knew what value would be a good value. Yeah, so there's a lot of like different variations on this attack possible. Yeah, absolutely. Okay. Okay. I think you got the idea. I think we desperately need a break. Does anyone else feel we need a break? Yeah, I think we need a break. So let's take a 5-minute break. For those of you here in the lecture hall, I'm going to put some snacks out here on the table over here. Come on up and help yourself. For those of you at home, maybe you have your own snacks. Nina. Yep. Yep.
Okay.
We're you don't have any information. So they gave us a large. You don't actually have.
Yeah, so you don't have, so even though you have extra space, you don't really have extra space. Okay, yeah. Yeah, so there's no check.
Unless you're playing people.
No, you guys.
Thank you for your yourself.
I mean, I kind of like. Guys are not.
Oh shoot. Well, maybe we screwed it up. Hold on. And I will look into that. Whether you really need lecture, lecture 5 or not. Isn't it? Yeah, I did something about it. Right. Okay. I don't. Off the top of my head. Thank you for catching that. I make a lot of mistakes. Thank you. Well, in this case, oh, sorry, yeah, okay, go ahead. Yeah, sorry, yeah. Yes, yes, yeah. There's another space for the argument. Yeah, exactly, like the drama. Yeah. No, in this case, if the argument is significant, then it's not a pointer, it just makes another copy of it.
And it doesn't matter if it's like, then this one actually wants to work.
Yeah, exactly, you got it. Hi. Yeah, yeah. Yeah, oh, it's out. We have on our policy page, the alternate exam is right after the regular exam.
So like mine.
Does that work?
I mean, my other class doesn't have any alternatives, so
Sorry, I know it's really late.
it's okay, I'll sleep in.
Okay.
How much do you get? It still looks like fun and.
There's like a little bit for each. For the, all right. Also, local variables. Yeah. Sure. Yeah, one more question.
It's like, say, I'm writing that, yeah. Or like, it's but how would they be?
The attacker can download their own copy. Look at what. And if it was an open source, so let's say it's Firefox. Yeah, but again, not open source. Put their own concepts.
If we have to somehow get like five VS code and like download the game.
Well, not your VS Code, it's the program running. It's not always.
I'm just like curious, it does seem like stack smashing is like the most common exploit, and if it's such a common thing, like why is it common for the stack to go down instead of, the stack goes up and the heap goes down?
We will see that stack smashing is only like, 10% of the problem.
Oh, yeah.
This is the first exploit that was discovered, and people were like, it's not too bad.
Okay.
And then they just found, oh no, there's a whole bunch of other, it's worse than we thought, so.
So
I'm like walking you through, we're up to like 1999 now. No worries, no worries.
We can learn about like Pegasus, so kind of the state of the art at any point.
Oh, I'm sorry. I gotta figure out what's going on over here. Something bad's happening. Only one.
Okay.
All right, let's reconvene. Let's get started again. Good job, everyone, with your snacks. You really smashed those snacks. Okay, I'm going to continue from here. Everyone on Zoom, if I didn't get to your question, I'm going to post on Ed an answer to your question. And for those of you here, if I didn't get to your question, I'll make a thread on Ed where you can post any questions I didn't get to and I'll answer them there. I've been talking about how an attacker could overwrite the RIP, and I kind of wave my part over this part about how does the attacker like arrange for malicious code that's going to do something bad to be in the memory address space. So let me just talk a little bit more about that. The most common way that happens is that the attacker writes some code to do something harmful, like reformat your hard drive or put a backdoor on your machine that allows them to log in as you, or emails a copy of all of your files to them or something. They write their own code to do something bad, and they compile it and assemble it to machine instructions. And then that is the malicious code that they arrange to have in memory, that they cause the program they're attacking to copy into memory. And there is a very common trick, which is to usually have a little snippet of code that first does some basic thing, like connect back to the attacker's server and ask the attacker's server for some code to run, and then runs that code. And so that's often called shellcode. You can go download on the internet shellcode snippets where people already wrote that code, just copy paste what they have, and put it in memory, and then overwrite the RIP to point to that, and it will now start executing the shellcode, and the shellcode will do the bad thing, like connect to this server and run what that server tells it to do or whatever. Okay, so we're going to assume that we have this shellcode. And it's not too hard to come by. And then of course, so what that means in terms of like the stages of an attack, the way that an attacker is going to exploit this vulnerability, if you have this bug in your code, they're going to find this kind of bug in your code, they're going to go look for it, and if they find one, then to exploit it, what they're going to do is they're going to somehow cause the program to do something that copies their malicious shellcode into memory somewhere. Maybe they provide the shellcode as their name or as some other input to the program, so the copy gets made in memory. Then they're going to exploit the bug, the buffer overrun vulnerability, to overwrite the RIP with the address of where that shellcode is stored. So they're going to have to be able to predict what address that shellcode is getting stored at. That's going to be one of the steps they'll have to do. And then when the vulnerable function, the function with a bug in it, returns, then the CPU starts using the overwritten RIP and transfers control and starts executing code at that address, meaning starts executing the malicious shell code, and now the attacker is won. Now the attacker has control of what that program, anything that program could do, the attacker now has the ability to make that program do. So if that program is running on your desktop machine under your username, then it has access to all your files, so that shellcode could read or write or delete all your files. Okay, so that's the stages of a buffer overrun exploit. So in this like toy example, we start with some shellcode that we got somewhere, downloaded off the internet, something like that. Let's assume it's only 12 bytes. Sometimes they're a lot longer than that, but let's just make it simple. And let's assume that this is in some widely used software. So anyone can download a copy of the software and run it in a debugger and figure out what addresses everything's are going to be stored in. And what the attacker might do is download their own copy, figure out what addresses of the stack frame is going to be at when this vulnerable function gets executed. Maybe they figure out the address where name will be stored when this function is executed. And then what they're going to do is they are going to arrange to have shellcode written somewhere in memory at a known address and arrange to overwrite the RIP with that known address. Where would be a really simple or convenient place for them to arrange to have shellcode put in memory? Put it in name. So when they supply the name, they can put the shellcode in name, maybe at the start of name. So then what an attacker would do is as input to getS, they would provide 12 bytes for the shellcode to get the beginning of name to be overwritten with the shellcode. And then they would provide some more padding, arbitrary bytes, spaces, or anything, could be anything. I'll say A's in this example. In this case, we need 12 of them. 8 more to fill up the name array to get to a total of 20 bytes in the name array. And then 4 more to overwrite the SFP. Didn't really matter what we overwrite it with. And then follow that with this address where the shellcode is at, which is the address of the start of name. So 4 more bytes containing that address, but in little endian form, so it looks reversed. So that would be the input to the program that the attacker would supply to this program. And the effect is, after this getS function finishes, memory layout would look like what's shown here on the slide. Okay? Then when this function returns, the CPU will jump to the address specified in the RIP, which is the address, the start of name, which is the address of the start of shellcode. So the CPU will jump to the start of shellcode and start executing it, and the shellcode gets run. Yeah. Can't hear you, sorry. What happens if you don't include the new line? Like in this case, getS function reads until a new line. If there's no new line, it'll never stop reading, I guess. I don't know. Maybe it stops when there's no more input available. But in this case, I just wanted to get us to stop so that this function would return. So I put a new line in there to make it stop. Yeah. And most shellcode's probably longer than that. So it's probably not realistically enough. So what could you do if your shellcode was longer than 20 bytes? Yeah? Just put it after. Where can the shellcode live? Anywhere in memory. As long as it's memory and the attacker knows the address where it lives, that's enough for the attack to succeed. So if there's not enough space in main, another place you could put it is after the RIP. So you could have like 24 A's and then this address you're overwriting the RIP with, and then the shellcode. How long a shellcode could that handle? What would be the limit on the shellcode, the max shellcode that you could handle in that way? Yeah? Yeah, like basically effectively unlimited, however much space there is for the stack. So it could be huge. Yeah. And if you don't like there, any other place that you can arrange for it to be in memory also works. But in this case, after is very convenient because I already have a getS function that is copying from the input into memory, do everything I need with just one using just that one input. Okay. Yeah. So the shellcode doesn't have to be at the start. It could be at the end of name. It could be after the RIP. Any of these are all valid. The main adjustment that you have to make is the address that you go in RIP has got to be adjusted to reflect where the shellcode is living in memory. Okay, so the attacker has a lot of flexibility on how they're going to do work out the details. I don't think I need to walk through the details. You can walk through, it might be a fun exercise if this is a little confusing, to walk through like what the CPU does when it executes each individual instruction in this vulnerable function and why that causes like the shellcode to get run in the way that I said it did. So that could be a fun exercise. The CPU doesn't know that anything good or bad is happening. It just executes each instruction and does what it's told to do, has no idea there's anything going wrong here. And the effect of executing these instructions when the RIP has been overwritten is to start executing shellcode. So I'm going to let you walk through that on your own if you want. All right, so that's the effect of having this kind of bug in your code. So that means that's really bad. These kinds of bugs are really bad. If you have this kind of bug in your code, you're opening up like a big security vulnerability. So that means we really better be careful when we're writing code to not have these kind of bugs in our code. So let's kind of check and do a little bit of like just testing our understanding, looking at some example code snippets. And I want you to look at this and tell me whether it's vulnerable or not. So here's another example. The only difference from what we were looking at before is now the name buffer is stored on the heap, not as a local variable. Is this vulnerable? How many say yes? How many say no? How many say help? I'm not sure. Okay, someone tell me a reason why it's not vulnerable. A reason that you might, like a reason you might come up with for why maybe it's not vulnerable. Yeah?
Oh, I think they're pretty starting. So if you start on the stack progression, like so that memory for name is stored in the heap. But I think the worst you do is like overflow the heap. But if we be able, oh, I guess you could like overflow the heap all the way up to it. That's in the stack, but I'm not sure if that's not direction.
Oh, okay. I just heard two interesting things there. Maybe not vulnerable because the overflight is in the heap, so you write past the end, you're just writing past stuff, we're overwriting stuff in the heap, but the RIP is not, it's in the stack, it's elsewhere. So maybe that's the reason it's not vulnerable. Or maybe it is possible to write past the end of the heap and all the way into the stack, and then you can overwrite an RIP. All right, anyone else want to give me any other reasons why this might be vulnerable or might not be vulnerable? Yeah, back there. Might be a memory leak. Okay, okay. I guess what I really want to know is, can the attacker run like malicious shellcode? That's like the worst case. Like the attacker gets complete control over this program. Oh my gosh, it's so bad. The attacker might be able to delete all my files, or like you do ransomware, or all sorts of nasty things, steal money from me. So I'm trying to, maybe I'm not so worried about memory leaks. I'm a little more focused on whether the attacker can run their malicious shellcode. Does that make sense? Yeah?
Program like has other key that it's like keeping like anything admin on that.
Oh, maybe there's other code that I haven't shown you that's storing other stuff in the heap that might be really critical, like has the user authenticated as admin or not? And then maybe that could get overwritten. That might be really bad. What would be another thing that could be stored in the heap that might be really bad? Yeah?
Could they do the whole like server thing that you were talking about earlier and kind of like access code outside of the system?
Well, the CPU is gonna, when it executes code, it's executing code in memory only. It's not gonna execute anything. Not gonna like execute stuff from across the internet unless that stuff from across the internet gets copied into memory and then the CPU jumps to that instruction. Okay, so you think there could be like an authenticated flag stored somewhere in the heap that maybe could be overwritten. I agree with that. Is there anything else that could be stored in a heap that would be dangerous if it was? What if you're an attacker and you're like checking to see what's stored in the heap? What would you be hoping for? It'd be like a really juicy thing to find if it were stored in the heap. Yeah. Password. Oh yeah. Oh, that'd be awesome. If I could overwrite the administrator password with like, let me in. And then I would know how to log in. I'd be able to provide the password and it would accept let me in as a password. What else?
You like, right there.
This could overwrite other variables on the heap. Yep. Turns out there's another thing that would be really juicy if there's a function pointer stored on the heap. Oh boy, that'd be awesome. That'd be awesome because then the attacker could overwrite that function pointer. And when that function pointer got called, could overwrite that function pointer with the address to shellcode. And that function pointer got invoked. Now the CPU starts running the shellcode. And it turns out that a lot of programs have function pointers stored in the heap. If you write C++ code, every object has a virtual table which has function pointers in it. So there's function pointer all over the heap. And it also turns out that even if there are no function pointers in the heap, these bad guys have come up with all these techniques to exploit this that are not at all obvious. But there's other pointers in the heap. If you find other pointers that the program's going to write to or read from, then you could arrange to overwrite one of those pointers so that it points to where an RIP is stored. And then when the program writes to that pointer, it's overwriting an RIP. And it turns out that the malloc, the heap data structures that are used to keep track of which regions are free and which ones are allocated, that malloc and free use, have some pointers in there. And the operations that malloc and free do are exactly just sufficient operations. So you don't even need any other code in the program. Just the fact that it uses malloc and free means that this can overwrite some like heap metadata used by malloc and free for the next object afterwards, so that when like you call malloc or free on that next object, it starts writing to a pointer, which then was overwritten and messed with. So now it overwrites a return address and like, the shellcode runs. So it's a crazy, hairy, complicated stuff how to do that. You can go look up how to do heap exploits, heap smashing exploits, and I don't want to teach you, but the bottom line turns out to be this is vulnerable code. This is bad. Already you should have a sense that this is bad from a security perspective, because I don't know what else might be in the heap, but it could be overwritten, so it's hard to evaluate how bad it is. So that looks kind of scary. But it turns out in essentially every program, it's just as bad as stack smashing situation. The attacker can run malicious shell. Okay, also vulnerable. Bottom line. Yeah.
Like, what's the general way that you can override other variables in the heap? Because my understanding would be that, like, you would start writing up into the heap as, like, the allocated space on the heap. And you could be writing, like, malicious code that garbage bytes.
It all depends where this object was allocated from in the heap. It could be anywhere in the heap. Who knows the order that things are stored in the heap? Okay. So what's the fix? The fix is don't use getS. Instead, use some function that is limited in how much it will write, so that it will never write more than the amount of space available that was allocated. Okay, so you call fgetS and you say don't write more than 20 bytes. And so, many of the standard C library functions will provide a way to specify how much space was allocated so that they will check and refuse to write more, right beyond the end of the space that was made available for them. Okay. So that's the fix. Basically, do balance checking to make sure that all of your accesses to these arrays or buffers are not outside the extent of the buffer. Okay, every library function is going to have a slightly different interface for how you pass these length values, or what length values you have to pass, or which library function you have to call. So you just got to learn how to do that. Here's another version way to make it safe is if you have an array, you can use size of. Size of returns the number of bytes that are allocated for that array. But it only works for arrays. It doesn't work if that's a pointer to a heap object. So it's kind of not perfect. And there's various C library functions that are designed so that it's easy to use them safely. GetS is a terrible design. It should never have existed. Stir copy is a terrible design. It should never have existed because it will copy without limit. But then there are versions of stir copy that have place a limit on how much they'll write that are designed to be safe. So you just learn what are the safe versions and how to use them safe. And if you want to learn how to use these library functions, you look at their manual page. And on Unix, you can run the man command, man space name of the library function, or you can just Google it. All right, I want to look at another type of vulnerability. Here's a crazy piece of code. It's got a buffer. It's copying data. I should tell you what memcopy does. Memcopy copies. The first argument is the destination, the second argument is the source. So in this case, it's copying bytes from the data array to the buff array. And it will copy len many bytes. And the question that I want to ask you is whether this code is safe or vulnerable. And I want you to talk to your neighbor and figure out whether this code is safe or vulnerable. So talk to your neighbor. But it's a different kind. All right, let's see where we're at. Someone want to give me a reason why safe might be what would be a reason for saying safe? What would be a reason for saying safe? You don't have to agree with the reason, just give me a reason. Awesome. Yeah, this does just what we want to do. We want to check the len to check how many bytes we're copying to make sure that we're not copying more than there's space available. What would be a reason to say it's unsafe? You don't have to agree with the argument. Just give me a reason someone might. Yeah. Yeah. So how many people here would vote safe for this one? And how many would vote unsafe? Okay, if you voted safe, I love it. That's great. This code is like trying to do exactly what you should do. It's like checking lengths before doing operations to make sure they're in balance. And if you voted unsafe, I love it even more because while this code is trying to be safe, it has a vulnerability. It has a vulnerability that has to do with this like obscure feature in C. And the obscure feature is the int. Is that a signed or an unsigned? Signed. So it could be positive or it could be negative. And if len is -1, it turns out, I know this is crazy. How would you know? Did the condition become true or false? Oh, false. -1 is not greater than 64. So this doesn't return. It goes on to do the memcopy. It does memcopy with the len as -1. And now the really obscure part, when you do memcopy with a len of -1, there's no way you could possibly know the answer, but I'm gonna ask you anyway. How many bytes does memcopy copy? Integer max. This is the really crazy part that I mean, this is a trick question. I didn't give you enough information to answer it, but it turns out that memcopy is declared, its function prototype declares its third argument is taking an unsigned int. And so the C compiler says, oh, I better cast that to an unsigned int. What happens when you cast -1 to an unsigned int in a 2's complement machine? Oh no, it becomes 2 to the 32 minus, let's see, 2 to the 32 minus 1, hex FFFFF, the largest possible integer. So memcopy tries to copy 2 to the 32 minus 1 bytes, like 4 billion some bytes. And that is way past the end of buff. So this code is actually not safe. How would you make this code safe? How would you fix this bug? Another if statement. What should the other if statement say? If len is less than 0, return. Yeah, check if len is positive or negative, and if it's negative, return. And that would fix this bug. Question. Yeah, how could a negative len be passed into this function? That's another part that's kind of a trick question. I didn't even show you how this function is called. Can this function be called with a negative len or not? I don't know. Maybe it can, maybe it can't. So maybe it's actually vulnerable or maybe it's actually not. If there's some caller who is like parsing some file format and it reads a length and it reads some data and the len comes from the file format, now the len could be supplied by an attacker. It could be, the file could be a malicious file we're reading vulnerable. Or maybe the caller only ever calls this with positive numbers and then it's not actually vulnerable. So we don't really have enough information to know whether this could be exploited in any given program. It depends on the context. But if the stars align in all the wrong ways, this could be vulnerable. So if you're writing this code, you probably shouldn't write code like this, where to tell whether it's safe or vulnerable requires a whole lot of extraneous stuff. Instead, you should write the code so that you have enough information to know for sure it's safe. So this would be bad code smell, at least, and maybe vulnerable. Yeah. Sorry, can you yell? Yes, you could also change it by changing the declaration of len to be an unsigned int. And then this typecasting, you could never be -1 and survive the length check and get cast to a really large number. That would also be another valid fix. There's multiple ways to fix this. So there's multiple ways to fix it, but I just wanted to point this out to you because it's like a really, really tricky kind of bug that's super easy to make. I mean, even when I'm staring at this example, I have to think a little bit to realize that it's vulnerable. And now if I've got 10,000 lines of code that I wrote today and I wasn't thinking about this at all, it'd be really easy to make this mistake inadvertent. Okay. Okay. So this is called a signed unsigned vulnerability. And it's a way that buffer overruns kind of rise when you're trying to do some length checks or some length calculations or something, but you didn't quite take into account the difference between signed ints and unsigned ints, and that they can get silently converted between them. That can cause subtle logic errors. So one fix is exactly as you said, use an unsigned int for the len parameter. And I think that's a really good practice that helps protect you from these kinds of errors, is if you make sure that your lengths are always unsigned, like they're type size t, which is an unsigned int type. Let's do another example. I want you to talk to your neighbor and figure out whether you think this is safe or vulnerable. Might this have a buffer overrun or not? Talk to your neighbor. Oh, and I should tell you, size underscore t, you can think of that as unsigned int. Only positive. Unsigned means 0 to. Okay, let's take a vote. How many of you are currently leaning towards safe? How many of you are currently leaning towards vulnerable? How many of you are currently leaning towards I'm not sure help? Okay, we got a good spattering. Then someone tell me some reasonable reason why you might argue safe. Yeah.
Uses like last position and terminating character.
Yeah. Yeah, we're gonna write, how many bytes we're gonna write? Len bytes for the mem copy and then 2 more. So this always allocates enough memory for whatever we're gonna write. Someone tell me a reasonable reason why you might argue not so.
The length is too big, like 2 power 32, and you add 2 to it. I don't really know what the behavior would be, but it might add some confusion.
Does anyone know what the behavior is if len is really big? You can yell it out. What does it do? Overflow, like wraps around. If let's say this is a 32-bit type. So if len is 2 to the 32 minus 1, what happens when you compute len plus 2? What number do you get? 1. Not 2 to the 32 plus 1, because that's too big, it doesn't fit. So the high bit gets just discarded. And it overflows and wraps around. Okay. Do we need more discussion? Or are we ready for a second vote? Does anyone want more discussion? You want more help? Let's take a second vote. You've heard a reason for and a reason against. How many of you say safe? How many of you say unsafe? How many say I need help? Okay, good, unsafe, yes. Because if len is 2 to the 32 minus 1, len plus 2 is 1. So malloc allocates space for 1 byte and succeeds. So buff points to an array in space for 1 byte. But then the mem copy writes 2 to the 32 minus 1 bytes. Way more than was allocated. Starts trashing everything afterwards. This has a memory safety vulnerability. It's writing past the end of the buff. It's writing out of bounds. Not safe. Okay, so I would say not safe. Don't write your code like this. Fix the code. How would you fix the code? How could you fix the code? Check. Do another check, yeah? Oh, wait, let me come back to your question. I just want to figure out how do we fix this first, and then I'll come back to your question. How do I fix this? So I don't have to worry. There's no chance it can write out of bounds. Yeah? Len has to be less than something. Yeah, less than 2 to the 32 minus 1, minus 2? I think minus 2. Maybe? I don't know, something like that. I think minus 2. You can use, there's this size max, which is the maximum value number that can be represented in this type. And if it's bigger than that minus 2, then there's gonna be an overflow. So put in a check to make sure that that will not overflow. Put in a check that will like cause this to just skip all the code if an overflow would happen. And as long as there's no overflow, this code is safe. Okay, now I know you had a question. I bet I can guess what your question is gonna be. Go for it.
Copy like the amount in data in this case, or does it try to copy all the way to length?
It tries to copy all the way to length.
Then it just
So it probably will crash, and probably no shellcode gets executed, I think. So maybe this is not catastrophic code, but man, I don't want to have any code like that where I have to start reasoning that I think there's no way to exploit it, even though it's writing out of bounds. One lesson I've learned is I've had too many cases in my life where I've said it's writing out of bounds, but I can't see any way to exploit it. Maybe it's okay. And then someone found some crazy way to exploit it. And so now I've learned if it's writing out of bounds, I'm just going to fix the code. I don't want to have to think hard. I don't know. I don't own enough aspirin. Yeah. I couldn't hear you. What wraps around? What wraps around is len plus 2. Okay? The number 2 to the 32 minus 1, that's a number. If I add 2 to that, in math, the answer is 2 to the 32 plus 1, but not in computer arithmetic. How many bits? So in this class, I'm just going to keep all our lives simple. We're going to have 32-bit architecture. So every register, every integer, every size t, they're all 32-bit types. That isn't necessarily true of any particular computer. Like my laptop, it's actually 64. But I'm just trying to pick some simplifying assumption for this class. How's that? Okay, okay. All right, let's keep going. I want to show you a case study. This is a fun one of my favorites, because I like to study elections and computer security in elections and like computers in elections. Just take a look at this story for a moment. Let me try to paraphrase for you what happened. There was some observer sitting there in a county headquarters watching like the votes get tallied, and the number was going up and up and up and up and up and up. And then it got to around 32,000 in this one precinct. And then the number started going down and counting backwards, counting down and down and down as more votes were coming in. And they're like, what? No, that's not supposed to happen. And when I heard this, I about fell over laughing. This is too classic. And why was anyone want to guess why I thought this was so funny? What does this have to do with what I've just been showing you here? Yeah.
They kind of hack themselves.
Yeah, it's not even a hack. It's just a bug. There's no security. It's not a security failure. But they kind of hacked themselves. Well, yeah. How does it even work? Yeah, it doesn't. What should happen? Yeah, what would you expect to happen as a computer scientist? Oh, you're puzzled by this part down here? Well, I'll come back to that one. Don't worry about that one down there. So what type do you think the number of votes in this precinct was stored in? What kind of? Assigned in, oh, like a 16-bit signed in. So okay. This quote is, this is a non-technical person explaining. So they got some details a little wrong. What did they get wrong? What actually happened? Went back to 0. What happens with a signed int when you get to the maximum possible positive value and you add 1? Where does it go to? Negative. Where's the highest number value for a signed 16-bit int? It's 2 to the something, right? What 2 to the what? 16? 15. 2 to the 15 minus 1. Does anyone know what 2 to the 15 is? 32,768. So the largest possible representable number in that type is 32,767. So when I see the number 32,000, I'm immediately suspicious. This is stored in a signed 16-bit int, meaning the largest possible representable number is 32,767. What happens if you add 1 to 32,767? What does it become? Negative 32,768. Does that sound like counting backwards? Well, it does, actually, if you look at it. Because if you look at what's going to be happening to the votes count, it's going to be 32,765, 766, 767, negative 32,768, negative 32,767, negative 32,766. But if you didn't notice the minus sign, it would look like it counted up to 32,768 and then went down from there. So this was exactly what happened. The people who built this software were like, we're making this for a polling place. You know, probably there's going to be like 100 people to show up. If like a lot of people show up, it might be 200. So like, oh my gosh, a 16-bit int is way more than enough. And then this county took this equipment that was designed for that and used it to count all the votes. I don't know, they had like a whole, portion of their county with tens of thousands of voters. It was way more than the designers anticipated would ever use this machine. And it was more than 32,767. And it sure enough, it had an integer overflow. And to the non-technical observers, it looked like it was counting backwards. And it added, and at one point, the vote total from this precinct, this collection, this portion of the county was actually a negative number. And they added that to the totals from other portions. And they got, many less than it should have been until they figured out what was going on. I'm like, okay. So many easy ways to fix this. Use an unsigned int, use a larger int. You check for overflow after adding. Super easy. But the reason I was laughing is because I could totally imagine making this mistake in my code, right? Like it'd be super easy mistake to make. So I kind of laughing in sympathy for the poor developers who are like, oh man, I'm sure they were kicking themselves after they saw this. And these kind of vulnerabilities are all over the place. It's not just like, bugs in elections, but it's also security vulnerabilities that allow people to hack, get root access on your Linux server and stuff like that. So for example, this is one security vulnerability in Linux kernel. You know what? For time reasons, I'm not going to go into it. This would be a fun thing to think about, like when you're walking through campus or you're standing in line at the post office or whatever, you're bored. I invite you to take a look at the puzzle on this page without sneaking ahead in the slides and try to figure out why. This was the bug fix. It was one line, changed from the red to the green. What was the bug with the red and why did the green fix it? You should know enough to be able to figure that out. Okay. So in summary, what I've been showing you is memory safety vulnerabilities. And there's all sorts of ways this can happen. They generally involve writing outside the bounds of some memory area. So stack smashing, writing outside the bounds of a stack allocated array and overwriting the RIP. But also can happen to heap allocated stuff. The fix to this is we write memory safe code that contains all the checks necessary to make sure that we never write or read outside the bounds of every memory region. And as a programmer, it's our responsibility to add those checks in there. And I showed you memory integer vulnerabilities, which can cause memory safety vulnerabilities. They're one common cause. As you start writing those checks, you might end up having to do arithmetic or comparisons on lengths. And if you're not careful, it's easy to make mistakes if you don't take into account like signed, unsigned, and integer overflow and wraparound semantics. So be careful of this common kind of mistake. I want to stop there and take a break, and then I want to continue with more types of vulnerabilities. Let's take a 3-minute break. You're welcome.
Makes a lot of sense. But I would say, that sounds really. Just in case, like when I was watching it, trying to like so they it's like visual skills. But she thinks it's like AI to really say.
I think this is gonna make it better. I thought when we write code, like point out that might be fun. Double check or suggest some details. It's not totally there yet. It's like that's all I don't know. No one knows. Everybody's debating this question. Yeah. Right now, it doesn't seem like there yet. I don't even see that. We're all trying to figure this out. Oh, I'm sorry.
I really like the current objects,
This class. Oh, no, the class I'll talk about. If you want to be more. There's lots of options. One thing. Capture the competition. Like cybersecurity problems. Often it's fun.
yeah, that's nice.
But might be a little easier after you've already done Python. Yeah. Oh, I haven't. I heard a lot of it. Actually, it's one of those classes right there. Unlimited amount of readings you can. If there's some topic you really enjoy, you can tell me about it. That's a lot. I'm gonna restart. I'm so sorry. I'll catch you after class if you want.
Yeah.
All right, we're gonna get started again. I wanted to show you some other kinds of vulnerabilities. I wanted to show you some other kinds of vulnerabilities here. beyond the stack smashing stuff. And I'm having a hard time estimating how to use time here correctly. So you can give me feedback about like if I'm going too fast or too slow on stuff, tell me so I can. I'm going to try to go fast for a little bit. We'll see how that goes. So I want to show you about format string vulnerabilities, which are another type of memory safety vulnerability that is maybe less common than the other things we've looked at so far, but is also a mistake that you can make. And you'll get some hands-on practice and experience with these in Project 1. So format string vulnerabilities have to do with this feature in C. Printf is a way you can print some output, and you can specify different values you want printed in, what format you want them to be printed in. So printf you can call if you're you call like example here, and the first argument is a format specifier. It describes what format the output should be in, and then the remaining arguments are some variables or values that you want printed. And in this format specifier, you can put a %sign and then a letter to indicate where one of those values should be placed. %s means a string. I want you to put a string at this place in the output. %d means I want you to put a number, d for decimal, at this place. And it will, the first %1, will be filled in with the first argument after the format specifier, and the second % will be filled with the second argument after the format specifier, and so on. So it's a fairly flexible way to produce output. There's no like checking of any kind in C though. So bad things can happen if the number of % in the format specifier does not match the number of arguments that were passed. So let me walk you through why that, like what happens, why, and then how this can lead to security vulnerabilities if you're not careful. Simplest example would be calling printf with a very simple format specifier and just one argument. Or %d, 1% thing, and one argument. How does printf work? This function will call printf. So when you call printf, that's just calling another function. So there's a stack frame that gets created for printf, and the code of printf runs. And when the code of printf runs, it starts looking for arguments. And in this case, printf can take any number of arguments. It's not a fixed number of arguments. So what printf does is it looks at the first argument, format specifier, and then uses that to determine how many other arguments it should be looking for. So if you look at the layout of the stack, the first argument to printf is right above the RIP. That has an address of the string that is that format specifier. And printf reads that string and says, oh, I see a %d in there. There's only one of those. So I'll go looking for one argument after this, and I'll print it out. And that one argument will be stored right above it on the stack. That's how where arguments are stored on the stack. If that string had %d, %s, %d, then it would go looking for 3 more arguments, not 1 more argument. It would treat the first one as a number, the next one as an address of a string, and then the next one as a number. So it uses the format specifier to figure out how many arguments are presumably, hopefully, present. Okay. What would happen if we called printf like this, but we forgot to pass the argument? Printf, it turns out, has no way of knowing. It reads the %d and it says, oh, must be one other argument. Let me look above where the format specifier is stored and assume that's the argument and treat it as the argument. But in this case, there was no other argument. So what it's actually reading is it's actually reading a local variable in the caller in func. So what this code will actually do is it will print 42. It will leak the value of this local variable because the local variable is stored in memory at the place where printf was expecting an argument to be, but there was no argument there. All right, so here's an example of code that is vulnerable. It has what's known as a format string vulnerability. It's a type of memory safety vulnerability. It's a way that can cause a memory to get written or read out of bounds. So in this code, what it does is it reads in some input up to 64 bytes. That part is not important. There's carefully linked checks, so they won't write past the end of buff. And then it calls printf buff. And presumably the intention of the programmer was to print whatever was read from input. But what's the bug? If the input contains a percent string, printf is going to think that's a format specifier and there should be some more arguments. It's going to go look for some more arguments. If there's 3% in there, then it's going to go look for 3 more arguments. And it's going to go looking on the stack and go like start printing stuff out on the stack. And that might be those values, who knows, it might just start printing out strange stuff that happens to be living at the stack at those places, which was probably not what was intended. So this could start printing strange stuff. So far, it doesn't sound like a very serious bug. I mean, it's a bug, but it's not a very serious bug. But I hope you agree it's a bug. Yeah?
Like the slide before it brings in 1, 2, 3. What would dereference memory addresses and then show you the value and expose the values of those, or will it pre-compact address?
Depends what format, what percent specifier is in the format string. If there's a %d, then it'll treat that part of the stack as an integer and print that integer. If it's %s, it'll treat that part of the stack as the address is string and start reading memory at that address and printing memory at that address. So, for example, if on the stack there happens to be stored the address of some place in memory where a password is stored, it'll start printing that password. Hopefully that doesn't happen. All right, so an attacker who's providing the input could specify any format string they want and cause this code to start printing stuff. Like printing any values that is stored on the stack. Well, not on the stack. Yeah, on the stack above this local variable. Could start printing out. There's not very much in this example that's probably stored on the stack, but if there was a caller that was storing something sensitive on the stack, you could start providing an input that was like %d, 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 and start printing a whole bunch of things on the stack. So this could allow an attacker to learn what data is stored on the stack. So here's in a way that an attacker could learn the addresses of things, even if they don't have access to the code of the program, if it has a format string vulnerability. But it turns out it's worse than that. Turns out it's worse than that. I'm going to skip ahead. And I'm going to skip ahead to a crazy case. One of the percent things that you can print in there, besides %d and %s, is %n. Most of the percent things cause printf to read memory and then print it. %n does something different. %n keeps track of how much has been printed so far and then writes to program memory the number of characters that have been written, that have been output so far, that have been printed so far. So %n says the argument should be a pointer, an address. Go store at that memory address a count of the number of bytes that have been printed so far. It's kind of a weird format specifier. It's rarely used, but sometimes programmers use it to keep track of like spacing and line things up in some, horizontal table or something like that. This turns out to be really powerful for an attacker because the attacker who controls that format string can put in there %n, and then whatever address happens to be stored on the stack at the place where printf was thinking an argument should be, will be treated as an address, and printf will write a value there. And that turns out to be really powerful. So let's take this example code and suppose that the attacker provides this input %d, %n. And let's look at what's going to happen. What's stored on the stack is buff, which is passed to printf as this format string. Buff is an address of that, where the string that was read in is found. Printf is going to read that, and it's going to find that what's stored in that string is %d, %n. So printf is going to say, there must be 2 more arguments there for me. So it's going to keep looking up the stack right above buff, the next 2 slots above that, to be the next 2 arguments. The first one is going to be an argument it's going to treat as a number and print that number out. So in this case, 42 is right above it. It's going to print 42. And then the next one's going to treat an address and write to that address. In this case, the address is address of the string where pancake is stored. So it's going to write something over the beginning of that string pancake. It's going to write a number, which is how many characters it's output. It's output 42. So it's going to write 2. Overwrite the beginning of pancake with 2. Oh yeah. So this number 2 gets overwritten on the top of secret string. So hopefully you can start to see how this is looking bad. An attacker is causing some memory in the program to get overwritten.
So here's what we provide as an input. Oh, so F gets as user input.
Yeah.
User provides this format.
Yeah. And because of the bug in the code, this code, how should that code have been written so it's not vulnerable? It's not buggy. What should they have done with that printf line? Yeah? Comma buff. Exactly. Printf %s, provide %s as the format string, and then buff as an argument after that. But they didn't do that. This is an easy mistake to make. As long as people are entering in inputs that don't have any % signs, it's going to look like it's working correctly. But as soon as someone enters in a % sign, strange stuff is going to happen. And if an attacker enters in just the right input, they can overwrite some of memory. In this case, they were overwriting the pancake. But it actually turns out that if you're really clever, you can arrange to overwrite like an RIP. Oh man. And then once the attacker can overwrite an RIP, they're in business. Do I even want to show you the details? Oh man, it's so painful. It's so painful putting together this exploit because it's so tedious and there's so many details. What happens is printf expects memory to be its stack frame and is going to interpret memory as its arguments. But there were no arguments pushed there. So the place where printf is looking for arguments is actually whatever else happens to be on the stack. And suppose our code looks like this, so it had some local variables on the stack. Then the place where printf is looking might actually be the contents of those local variables. And if the contents of those local variables were inputs that were read in, an attacker could control them and specify what gets stored there. Then some of the values on the stack might be controlled by the attacker. So when you have a %n and printf says, let me find an address and write something there, that address might be from a part of the stack that was actually data that the attacker provided. So printf will go writing to an address that the attacker provided. Could have been like the address of RIP. So for instance, if attacker wants to write the number 100 to memory address dead beef, what the attacker can do, oh man, this is crazy, is provide this input. Provide this input that has dead beef and 94C, %94C, and then %C, and then %C, and then %N, and oh my gosh, let me show you what's going to happen. The program reads that input into buff, which is stored on the stack. So I've updated the stack with those values that were copied in. Now printf reads that format string in buff and says, let's see, there's 1, 2, 3, 4 arguments. So it starts looking for 4 arguments. And the first argument should be treated as a character. So the first argument is arg1 marked over there, and it's going to print out whatever's stored in the stack at that location, which in this case is the first 4 bytes of str. I don't know, it could be anything. And then it's going to print the next %c will print the whatever's stored in the next 4 bytes of str, and then the next %c will print whatever is stored in the next 4 bytes of str, but like interpret it as a character. And then the %n will be looking at arg4, the region marked arg4. So it'll like say, I need to write to some address. It'll go look at the place that I marked arg4 as where that address is stored. It's going to interpret that as the argument to printf. In this case, what's stored on the stack there is, well, that's the beginning of buff, and we arrange the beginning of buff held the bytes deadbeef. And so printf is going to read the address deadbeef and going to go start to write something to deadbeef. And what does it write? It writes however many characters have been output so far. And how many characters have been output, you can count how many characters are output by each of these things that it's printing. And the %94c says print a character, but add spaces to make it 94 wide. So this is actually printing like, I don't know. I can't even count. I think like 100 characters if you add it all up. And so then it'll write the number 100 to the address deadbeef. If I lost you, try to check this out after lecture. I'm sorry. I know it's really complicated and tedious, but the end result is that at the end, the attacker was able to write a value that they chose, 100, was arbitrary, could have been any other number, to an address that they chose, deadbeef, could have been any other address. You could modify this to write to any other address you wanted and to write any other byte value. So this gives the attacker the ability, if the code has this bug, to pick any address in memory and arrange that any value they want is written to that address. Any 1 byte value is written to any address that the attacker wants by exploiting this bug. And actually, the attacker can do it multiple times. So if you were the attacker and you had this ability and you're like, I don't understand how it works, but I know that I can pick any address I want and any byte value I want and write that byte value to that address and do that multiple times. How could you use that to run malicious shellcode? What would you do from there? Yeah. You could write the shellcode in bytes at a time, okay. But now I want the shellcode to get executed. So what's the next thing I got to do? After the shellcode gets stored in memory somewhere. Yeah.
Know the system well enough to know what arguments stack where. Also add extra format strings so it's more arguments and
overwrite the RIP with the address of where that shellcode is. Except the RIP is 4 bytes, and I only get a way to write 1 byte. Do it 4 times for the 4 pieces of the RIP, and then I'm in business. So you can see how these exploits get really complicated. Oh my gosh, this is super messy. And I will let you work through the details, or you can just trust me that this is possible. And then rediscover it in project 1 for yourself. You'll get to reinvent it. Okay, so if your code has that kind of vulnerability, it's probably also host. You're probably also host that shell attacker can run arbitrary shellcode. So don't write that vulnerability. Fix your code in the way that we previously mentioned. Don't pass a user-controlled input as the format string. Make sure the format string is always constant. User-controlled things should be in the remaining arguments. Okay. So an implication is if your code has this kind of bug, this format string bug, then an attacker can write any byte value they want, anywhere they want, repeat that multiple times. This is enough to override RIP, override a function pointer so they can run arbitrary malicious shellcode. And this is the kind of thing we see a lot in software security, where if you make this class of bugs, it allows the attacker this capability, write any byte anywhere or something like that. read any byte from anywhere, and then by putting those little building blocks together, they can ultimately arrange a whole sequence of operations, and then in the end leads them to run arbitrary shellcode. And I'm giving you an example of a catalog of types of common mistakes that you can easily make in your code that then open up a security vulnerability. On first glance, it just looks like a bug that might cause your program to output weird stuff, but on deeper inspection, turns out to actually allow an attacker to take control of your program and completely hose you. Okay. So there's lots more. This is like an area that's super, super deep. There's tons of these classes of vulnerabilities and tons of exploit strategies to get really fancy and clever. And one example is, I'm not going to talk to you about it. If you're going to overwrite a heap buffer, you can overwrite like C++ V tables and do lots of terrible things. And I'll let you look at slides if you're really curious, but like it gives an attacker a lot of power to do terrible stuff. So one of the bottom lines is, if we look at the top most common ways that software has been vulnerable, the top 10 list in 2023. And of the top 10, 3 of them are memory safety failures. They're types of memory safety screw-ups that cause you to write, that enable, well, they're bugs where the program might write or read outside the bounds of an array or buffer or memory. So these are very common and prevalent. It's an easy bug to make if you're writing in C, and it has very severe consequences if you do have that kind of bug in your code. And it only takes one of them. If you've got 1 million lines of code in your software, and one of them is vulnerable like this, and it's handling some untrusted input, that's enough that someone can hack your software, maybe take control of your computer. So it sucks. Okay, and these exploit techniques can get really, really clever. They're so nifty. And there's one that I would love to show you, but I'm going to spare you from, because like 3 hours is so long, and the last thing I need is another 20 minutes on some incredibly intricate technical attack. And it's not the most important thing in the world. It just blew my mind when I saw it. So I'm going to give you the TLDR, and I'm going to let you look through the slides if you're curious. And I think we have an exploit in the project where you're going to get to work through this in detail. So when you get to that part of the project, you might want to come back to these slides or this part of the textbook and like study how an FI1 exploit works. So far, I've been talking about attacks, exploits, where there's some bug that enables the attacker to overwrite a whole bunch of stuff, and all the way up to and including an entire RIP. So in these examples, it required writing 8 bytes past the end of the buffer. 4 bytes to overwrite the SFP, and then of the 4 bytes to overwrite the whole RIP. And many bugs have that form. Didn't have the right length. There were no length checks in there. Attacker can write as far as they want. Certainly they can go 8 bytes. Sometimes there are some bugs where the code has some length checks in there. Developer was like taking care to avoid any kind of buffer overrun bug by doing some length checks in there, but they screwed up and they have an off by 1 bug. And an off by 1 bug in their logic and the checks they do that enable the code to write 1 byte past the end of the buffer, but not more than that. So this would be a dumb example. This code on the left is a dumb example of an off by 1 bug. It's not very likely to happen, but there are other ways you could easily have a logic bug that has off by 1 error in it. In this dumb example, this program will read up to 21 bytes from the input and write it to a buffer, but the buffer only has enough space allocated for 20 bytes. When I first saw an off by 1 vulnerability, my immediate reaction was, oh, that's a bug. You better go fix that. But there's no way someone's going to be able to exploit that, because you can't get to the RIP. 1 byte past the end isn't enough to overwrite the RIP. You would need 4 bytes past the end. Kind of need 8 bytes, but maybe 5 bytes would be enough. You know, if you had 5 bytes, you could get 4 bytes to overwrite an SFP and overwrite at least 1 byte of the RIP. maybe you'd be getting somewhere, but here, this is not 5 bytes, it's only 1 byte. So all an attacker can do if they provide a malicious input is overwrite 1 byte of the SFP. They can't overwrite the RRP. And this exploit technique shows that in some cases that is enough for the attacker to execute arbitrary malicious shellcode. What? How is that possible? It seems impossible that overwriting 1 byte of the SFP should be enough for the attacker to completely gain control of your program. Like if they overwrite 1 byte of the SFP, then they've got the wrong SFP. So when the function returns, EBP gets restored to a wrong value. The stack frame, EBP determines where the stack frame is. So now the program is going to start looking in the wrong place for the stack frame. Seems like the program's going to go haywire, but it's not going to lead to execution of malicious shellcode. And moreover, it's not that the EBP is moved to anywhere arbitrary. It's just 1 byte. The first byte has been overwritten. We're in little endian, right? So the first byte is the least significant byte. So the EBP that gets restored will be almost correct, except the least significant byte will be wrong. So the EBP will get restored to something that's maybe a little too high or a little too low. And actually the attacker in this example has even less control than that, because remember strings in C are null terminated with a null byte. So if you try to provide a long input, what happens is fread automatically makes sure that the last byte is a null byte, is a 0 byte. So the attacker can specify 20 bytes, which go into name, and then a null byte, which gets written into the low byte of the SFP. So all the attacker can do is replace whatever was in the low byte of SFP, the least significant byte of SFP, with a 0. So now the EBP, instead of pointing where it should be, it's pointing somewhere smaller, right? Whatever that least significant byte should have been, it became zeroed out. So that makes the number smaller. So smaller goes down. So now EBP is pointing lower than it should be. And now the caller is looking for its stack frame, not where it should be, but somewhere else further down. Oh, maybe you got an idea. Ooh, I see an ooh. So what the attacker is gonna do is gonna hope, just hope, that that lower place where that lower stack frame points down to lines up in just the right spot with like name. So that the caller, when the caller starts executing, where it's looking for its stack frame is not in the right spot, it's down in name. But it's interpreting whatever is down in name as a stack frame. Maybe you can get a sense that bad things could happen if it starts interpreting that memory down in name as a stack frame. When the caller returns, it looks like at the top of its stack frame for the saved EIP, for the RIP, and it jumps there. So it's going to think that there's an RIP stored down there, but that's in the region of name, maybe, if we got lucky. And the attacker can provide an input in that controls what's in name. So if we're really, really, really lucky, when the caller returns, when this code returns, it goes to the caller. When the caller returns, it's looking in the wrong place for the RIP, and the place where it looks might just be a place that has a value that the attacker supplied, and so the attacker could supply the address of shellcode. So basically, the attacker arranges that the memory, this region of memory that we call name, gets interpreted as a stack frame containing things like an RIP, and the caller there goes and uses that and transfers control there. And there's so many details to work out to make this attack work. But it blew my mind that an attacker with such a tiny mistake in your code, an attacker with such a tiny bit of control over memory, over just 1 byte and just with a 0, was enough to execute malicious shellcode. And ever since then, I've been like super paranoid about any memory state vulnerability in my code. About it could be really bad. Okay, question. Yeah, what are the conditions for this to work? If the code of the caller and the callers and the callee are just, I don't know, if everything works out right. What do you mean by works by itself? Maybe tell me again. Tell me more about your question. Yeah. No, usually there's a way to get malicious shell code into memory. Maybe not in this example, but often programs read a lot of inputs and they store them in memory. And so I arrange that any of the other input that is read have the contain shellcode, and then it will now be in memory. So like, for instance, if this is, I'm entering in my name and I'm entering in, what file this should operate on, and I'm entering in my email address and so on, I might provide one of those to provide malicious shellcode as the input to one of those, and somehow figure out where in memory that's going to get stored. And then this other one that's read in this vulnerable way is the one where the exploit kicks off. Yeah. Okay, so I don't expect you to understand all the details of that because I didn't walk you through all the details of that. You can see it in loving detail in the slides on your own, or you can go see it in the textbook. Let me do two last things and then we'll call it quits and I'll take questions afterwards. I wanted to tell you about a trick that when you're writing exploits, you can use to make them more reliable. One of the things that many of these exploits require is knowing the address where the shellcode will be stored and then putting that address into overwriting the RLP with that. It might be that sometimes it's hard to predict exactly what address the shellcode will be stored at, or it's kind of tedious and annoying to figure out exactly the address, but you can figure out roughly what it is. Then there's a trick to help you. And the trick is called a NOP sled or a no-op sled. And the trick is you use shellcode that's a little bit longer, where the first few hundred bytes have no-op instructions. This is a 1-byte instruction. And your shellcode starts with a few hundred of these no-op instructions. And then is the actual shellcode. So now if you do this kind of shellcode, turns out you don't need to overwrite the RIP with the exact start of your shellcode. Just any address anywhere in the middle of this no-op sled, pointing to any of these no-op instructions will be good enough, because it'll start executing that no-op and all the other no-ops. Each of the no-ops does nothing, and then it starts to execute so it's like you created this long landing pad, and as long as the address lands anywhere in that landing pad, the exploit will succeed. And there's a bunch of tricks that hackers have come up with to make these exploits more reliable. So in summary, there's a whole class of vulnerabilities we call memory safety vulnerabilities that have to do with, you have a bug in your code that can cause the program to read or write outside the bounds of some memory region. And these have a very severe impact. Often they can be exploited by attackers to take control of the program and maybe of your computer. So you really don't want to have these vulnerabilities in your code. And next lecture, we'll look at defenses that people can use to protect themselves against this common kind of error. Thank you so much for sticking with me.
We don't equal bias to make sure that our show